Howdy, this is your friendly neighborhood physics teacher here, and I'm here to talk about 2D motion review. So, your test is on Friday. I am starting on page 3. Page 1 and 2 go over some key points of 2D motion. But I'm going to let you read that on your own. I'm just going to start on questions. So, question number 1. A horse was running at 8 meters per second and is accelerated 3 meters per second squared for 15 seconds. What was the horse's final speed? So we're going to do our givens. So our first given is this 8 meters per second. So that meters per second tells us that it's a velocity. Knowing your units is a key thing. And is accelerated at 3 meters per second squared. So acceleration is A. So 3 meters per second squared for 15 seconds. Seconds tells us that is time. What was the horse's final speed? So our unknown is final speed. So if we're looking for final speed, what do you think this speed over here has to be? Initial. Our equation we're going to end up using is VF equals VI plus AT. Now, I understand that on your formula chart, your formula is probably going to look like VFY equals VIY plus AT. But that Y is just telling you it's in the Y direction. Guess what? You can change that Y into an X. Ba-boom, ba-boom. You have your equation. So we can plug in what we have. We're looking for final velocity. Our initial velocity is 8. Our acceleration is 3. And our time is 15. So now we have to, now it just goes into algebra. After you plug in, it just goes into algebra. You have to multiply first. Remember PEMDAS, so you just do 3 times 15, and you get 45. And then you add 8. That gives you 53 meters per second. And that is your answers. That's how fast the horse was going after it accelerated. So number 2. The tennis ball was hit with initial velocity of 12 meters per second at an angle above the horizon. It remains in the air for 4 seconds. Which quantities stay constant? So which quantities stay constant while the tennis ball is in the air? So we have a ball that's being launched. Boom. And we want the things that stay constant. We want the items that do not change. That's what constant means. Do not change. Do not change. So items that do not change. Hopefully the first thing pops into your head is acceleration due to gravity. And the second thing that pops in your head is your velocity in the x direction is constant. Now, since velocity in the x direction is constant, what does that mean for your acceleration in the x direction? Hopefully you said it's 0. Is your velocity in the y constant? No, it is not. So these are your 3 main things that stay constant. Acceleration due to gravity, which is in the y direction, and your velocity in the x, which is in the x direction, and then your acceleration in the x direction. Since we have both accelerations, we have acceleration in the y, and we have acceleration in the x, that means the overall acceleration, acceleration vector. Acceleration vector is also constant. Acceleration vector is also constant. Is our velocity vector constant? Is our velocity vector constant? Hopefully you said no. And it's because our velocity in the y is not constant. Yes, our velocity in the x, but the vector deals with both velocity in the y and velocity in the x. But our acceleration vector is constant because our acceleration in the x and acceleration in the y are both constant. So number 3. A roofer threw a shingle off a roof with an initial horizontal velocity of 3 meters per second. A shingle lands after 2 seconds. What horizontal direction did the shingle travel? So our givens. All right, so it is a horizontal, so that's velocity in the x. Horizontal is x. So our initial horizontal velocity is 3 meters per second. Do we need to put that I there? Is that initial important? Not really, because it's constant. Constant. So that initial doesn't really matter. The shingle lands after 2 seconds. Seconds is time. What horizontal distance are known as horizontal distance? Again, horizontal is x. Horizontal is x. So we look at our equation sheets. You'll see that delta x equals Vx times time. Now remember, this is the only equation in the x direction. This is the only equation in the x direction. There we go. So you get 6 meters. Oops. There we go. That is our answer. I forgot to highlight this answer. There we go. So number 4. An archer shot an arrow with an initial velocity of 22 meters per second and an angle of 70 degrees. The diagram shows the path of the arrow. What is the horizontal displacement of the arrow when it reaches point 3? So point 3 is right there. And if we look at our drawing, point 3 is on the same level as what it's being launched at. So what's so special about this point and this point? It's the same, so it's the same magnitude, because magnitude just means number. Same magnitude, different direction. So same magnitude, different direction. So let's pull out our givens. So our givens, we have a velocity with an angle. Anytime you have a velocity with an angle, you should automatically think triangle. So when you see a velocity with an angle, you should think triangle. So that velocity is just our initial velocity. No direction, because it's going in both directions. Give us our degrees, which is our angle. And our unknown is looking for our horizontal displacement. So the equation we're going to end up using, because we're looking for horizontal displacement, is our velocity of x times time. We don't have either one of those. So we need to figure out how to find that. Now, to find our velocity in x, if we have a velocity at an angle, to find our velocity in the x, we are just going to draw a triangle. Because you should be thinking to draw a triangle. So this becomes your initial velocity here. This is our velocity in the x. This is your initial velocity in the y, and that is your degree. So this initial velocity is 22, and our degree is 70 degrees. So to solve for our velocity in the x, we're just going to use our initial velocity cosine angle. Solve for our initial velocity in y, we're just do initial velocity sine angle. I was able to figure out those because this is your hypotenuse, this is your opposite, that is your adjacent. Sine theta equals opposite over hypotenuse. If we plug in what we got, our opposite is initial, our hypotenuse is 22. When you get this by itself, so you multiply both sides by 22, so your initial velocity is 22 sine of theta. Initial velocity sine theta. So you don't have to go through these steps. I'm just showing you where it comes from. And this one comes from, if you go to cosine, is adjacent over hypotenuse. Your degree is 70. Accelerate, your adjacent is velocity in the x. Your hypotenuse is 22. Again, to get it on the other side, just multiply. So your velocity in x ends up being 22 cosine 70. And you just plug that into your handy dandy calculator. So you get 20.63 meters per second for your initial, and you get 7.52 meters per second for your velocity in the x. So we just figured out our velocity in the x. So that's going to go there. But we still need time. We still need time. Since we know our initial velocity, we also know our final velocity, right? Because this statement right here, same magnitude, different direction. So our final velocity becomes a negative 20.67 meters per second. Since we have our final and our initial, we can use the final velocity in the y equals our initial velocity in the y plus AGT. Because part of our givens, we always have acceleration. And that's an A. So our final velocity is a negative 20.67. Our initial velocity is 20.67 plus negative 9.8 times t. We need to get t by itself. You cannot do anything with those two. That can't do anything. No, can't do anything there. So I don't want you to multiply that. So you can't do anything there. So we need to subtract this 20 over. So you're left with a negative 9.8 times time over here. And then you have a negative 20.67 minus a 20.67. So that gives you a negative 41.34. To get t by itself, you divide, and this is why your 9.8 has to be negative, because if not, you end up with a negative time. Can you get a negative time? Hopefully you say no. And your time is 4.22 seconds. So now we can use this time This time there. So you plug in. So our velocity is 7.52. Our time is 4.22. You plug that into the calculator. And the arrow goes 31.72 meters. That is your answer. So yes, it's just asking for one thing, but you kind of had to do 1, 2, 3 steps before you could even solve for what you did. If you see a velocity at an angle, go ahead and draw your triangle. You're going to need it. Remember, if it's at the same height, the magnitudes are the same, just different directions. So since you knew your initial, you knew your final, it's just negative. And you're able to use that information to solve for your time. Next question. A volleyball is thrown directly upward at a velocity of 5 meters per second. How long does it take the volleyball to reach maximum height? Now, if you see maximum height, what happens to the velocity at maximum height? We're doing givens here. What happens to the velocity at max height? Hopefully you know that velocity at the top is 0. So that's when max height happens. It also gave us our initial velocity is 5 meters per second. So if we want max height, that velocity at the top also equals our final velocity, because we're just going here. That's all we're going. That's all we're doing. We're just doing there. We're just going to max height. And as a given, we always have acceleration due to gravity. That's always there. So our unknown, we're looking for how long. How long, you should realize that. If you say, like, how much longer is this class or anything, you're looking for time. So the equation you're going to end up using is that good old one we did over there, your final velocity equals your initial velocity plus AT. Your final velocity would just be 0. Your initial velocity would be 5. You have acceleration due to gravity, looking for time. Again, you can't do anything right there, so you have to bring the 5 over. So you get a -5 equals a -9.8 t. And you divide by 9.8. So your t ends up equaling 5 divided by 9.8, -5 divided by -9.8. So it takes about 0.51 seconds. 0.51 seconds to get there. There we go. So now number 6. A volleyball is thrown directly upward with a velocity of 5 meters per second. What is the volleyball's maximum height from its starting point before it begins to fall back down to earth? So I have the same exact givens. So we have our final velocity, because again, we're dealing with max height here. Since we're doing with maximum height, our final velocity is just going to be velocity at the top, which is 0. Our initial velocity is still 5 meters per second. We have acceleration. So our unknown is maximum height. So it's our delta y. So you can use the time if you want, but say what we have here. So we have final velocity. equals initial velocity plus 2ag delta y. So I have everything but delta y. Final is 0. Initial is 5 plus 2 negative 9.8 delta y. So we can go ahead and square it. So 0 squared is just 0. 5 squared is just 25. And 2 times negative 9.8 is just a negative 19.6. So again, you can't do anything right here, so we need to bring the 25 over. Give me some space. There we go. We bring the 25 over, so we get a negative 25 equals a negative 19.6 delta y. To get that by itself, you divide. So you do 25 divided by, or negative 25 divided by negative 19.6. Again, that 9.8 needs to be negative. And you get a 1.28 meters. You get 1.28 meters. There you go. That's how you find max height. So number 7. A basketball is projected at an angle of 20 degrees above the horizon with a velocity of 12 meters per second. What will be its approximate horizontal displacement across the level surface? A little bit more here. Go. Write out our givens. So we are given the angle 20 degrees above the horizon with a velocity of 12 meters per second. So that 12 is our initial velocity, even though this wording right here, so it's at an angle of 20 degrees above the horizon with a velocity of 12 meters per second. What that means, if this is the horizon, you're 12 degrees above it. That's all what that means. Just 12 degrees above it. What is approximately horizontal displacement? So our unknown, we're looking for delta x again across the level surface. So again, so if you see a velocity with an angle, you automatically think triangle. I put 12 there. I should have put 12 there. I meant to put 20 there. That should be a 20. There we go. And 12 here. So our velocity in the x is in the horizontal direction. Y is in the vertical direction. So we can just use VI cosine theta, VI sine theta. Our VI is 12, sine of 20. So you get our initial velocity in the y to be 4.10 meters per second. Our velocity in the x would be 12 cosine of 20. And that will get you 11.28 meters per second. So that's our velocity in the x. That is our initial velocity in the y. So our equation is delta x equals vx times t. So we have our vx now. So that can go here, but we need our time. That goes back saying if you know your initial, you know your final. It's just a negative 4.1 meters per second. And you can use that same equation that we have been using for like the past 3 problems. So our final is negative 4.10. Our initial is 4.10. Our acceleration is negative 9.8 t. Can't add or subtract there, so we need to bring this over. So that gives you a negative 8.2 equals a negative 9.8 times t. And then you need to you'll need to bring over your negative 9.8 and you plug that into your handy dandy calculator. And you get a 0.84 seconds. So now we have time. We can plug in what we have to solve for our delta x. So delta x is 11.28 times 0.84. And you get a 9.44 meters. And that is your answer. There we go. Number 8. Which trial from the table below with an will the object have the greatest horizontal displacement? So which will have the greatest horizontal displacement? So again, we're looking for horizontal displacement. So we're looking for delta x. That's what we're looking for. And we have our velocity, and the angle. So these are all little triangles here. Tons and tons and tons of little triangles. Our angle, our initial velocity in the x, and our initial velocity in the y. So basically, for each one of these, you're going to do this setup, what we did before for number 7. You're going to find your initial and final velocities, and then potentially, if you can't see it from there, you can find time and then solve for your delta x. So I'm going to go through trial 1, and we're just going to find our our velocity in the x and our initial velocity in the y. This is 10 cosine of 10, 10 sine of 10. So 10 cosine of 10, that just gets you a 9.85 meters per second. 10 sine of 10 gets you a 1.74 meters per second. So trial 2. Trial 2, we have again initial, cosine, initial, sine. So you have 20 cosine of 45, 20 sine of 45. So our velocity in the x will end up being 20 cosine of 45, so that'll get you a 14.14 meters per second. Our initial will give you a 20 sine of 45. Oh, look, it gets you the same answer. Anytime you're dealing with 45s, it's a perfect, so you're 45 degrees here. So you're 45 degrees here. It's a perfect half of 90, right? So this is 45, and that would be 45. So since it's a perfect half, that's a perfect, it's half of a perfect square. So remember squares, what's so special about squares? Squares have to have the same sides. So anytime you're dealing with 45, you only really need to do one of them because it should be the same. It should be the same. So then our number 3, velocity x is initial cosine, initial velocity y is initial sine. So number 3, we have 30 and 60. 30 and 60. Our initial velocity y, 30 and 60. We plug that in. We have a 30 and 60, so that gives you 15 meters per second. And you do a 30 and 60. That gets you at 25.98. And for number 4, the exact same thing. One last time. Whew, okay. So for number 4, our initial is 40 and then 90. 40 cosine of 90. Initial is 40 sine of 90. You plug that into your calculator. 40 cosine of 90. Oh, that gets you 0. And if you do 40 sine of 90, oops, helps if I actually put it in right. Let's try that again. And that just gets you 40 meters per second. Anytime you're going 90, that means you're going straight up, right? So you have nothing in the x direction. So looking at our data, first one you should eliminate right off the bat is number 4. Number 4 is not right. You should eliminate number 4 right off the bat because it's 90 degrees means it's just going straight up. That's 90 degrees, it's just going straight up. So now let's look at our numbers. We have about a 10 and a 2, 14, 14, 15, 25. So basically, if you just look at the numbers and which ones have bigger numbers is going to be your answer. So you don't have to sit there and do the other steps if you don't want to. So your answer is going to end up being number 3 because you're going to end up multiplying 15 by however long it takes. You can solve for your 25 there. So after you look at that, look at your bigger numbers, and it'll end up being number 3. So there we go. Number 9. Miss Verona is doing a demo for your class. She had 2 racquetballs that were the exact same size and mass. She drops one off her tall podium from rest and flicked the other one with a horizontal velocity of 0.5 meters per second. Both racquetballs move at the same time because Miss Verona is awesome like that. How long after the first, splash is the second splash? I didn't mean to put the word splash. Is the first bounce. Let's try that again. Is the second bounce. So basically, how far apart are the two bounces? So if we have a podium, we have two balls that are at the same height, and one is just dropped. And then the other one is launched. Which one would hit first, basically? Which one will hit first? Ball 1 or ball 2? And if one does hit first, how long after the splash? But remember, the main factor of time is height. Height affects time. So since they're at the exact same height, their time is going to be the same. Same height, same time. So how long before they bounce? 0 seconds, because it's the exact same. Same height, same time. Same height, same time. That little velocity in the x going this way does not affect time. Your velocity in x does not affect time. Your main factor is height. So number 10. Two students were practicing for a play where the male lead needed to toss a rose at 14 meters per second at an angle of 60 degrees to the female lead from 1.3 meters above the ground. If it takes 1.23 seconds for the female lead to catch the rose, about how high above the ground did the female lead catch the rose on the balcony, assuming air resistance? So the most tricky thing right here is this right here. So that is this, 1.3 meters. But what we're looking for is all of that. That is what we're looking for. But what the projectile starts here. So this is our delta y. This is what we're looking for. So you need to get that, you need to take your delta y and add it to this 1.3 meters. So that's when people miss a question like this, that's the part they're missing. So let's pull out our givens. So it's being tossed with an angle of 60 degrees. And it is, so we're just going to say, so it's above, so we're just going to put that as just plain y. We have time, 1.23 seconds. What we're looking for is our delta y. So we're looking for our delta y. You see a velocity at an angle, you should automatically draw your triangle. So 60 degrees, initial velocity, velocity x, initial velocity in the y. So this becomes just initial velocity cosine angle, initial velocity sine angle. So initial velocity is 14, cosine of 60. This is 14 sine of 60. Just plug that into your handy dandy calculator. Cosine. So that gets you 7 meters per second. And this gets you 12.12 meters per second. since we know our initial, we know our final. Well, oh, hold on. We know our final if it's being thrown completely, but is this one being thrown completely? No, it's going from here to here. So what would be our final? That's part of our givens. Right, our final velocity is 0 because she's catching it at the top. And don't forget, we do know our acceleration due to gravity. So our final is 0 at the top. Our 0 at the top. So we have our initial, we have our velocity in the x, and we have our final. So our equation that we can use, we didn't necessarily even need our velocity in the x, if you realize that, but it's just habit to do both. So it'd be our final velocity in the y equals our initial velocity in the y plus 2ag delta y. So final would be 0, initial would be 12.12 squared plus 2 negative 9.8. We're looking for delta y. 0 squared is just 0. 12.12 squared is 146.89. 9.8 times 2 just gives you a negative 19.6 delta y. We can't do anything mathematically here, so we got to bring this over. And what we do to one side, got to do the other. And you just divide. 0.89 divided by 19.6. So your delta y is 7.49 meters. Now, are you done? Are you done? No, you're not done. We have to do something with that 1.3. That, your delta y is just where he threw it to where she caught it. So before you answer, you need to add that 1.3 there. You need to add that 1.3. So your answer would be 8.79 meters. So that is your answer. Now you can pick your answer. Oops, not what I meant to do. Okay. Alex was taking a break from studying for his physics exam and walks the duck pond. Alex decides to go to the bridge and toss rocks into the pond. The bridge is 0.34 meters above the water. The rock lands 2.4 meters away from the bridge. So our givens. We have the bridge is, so as our delta y, 0.34 meters. And he tosses it 2.4 meters away. So since it's someone on a bridge and he's tossing them, that's going to be your horizontal projectile. So we're dealing with projectiles in the horizontal. We're dealing with projectiles in the horizontal. So the first question is, the ball is in the air for. So we're looking for time. What's the main factor of time? Yes, height. Oh, and don't forget, we do have acceleration as a given also. So we're looking for time here. That is our unknown. So the equation, we're going to end up using is delta y equals 1/2 agt squared. We know our delta y, t squared. There's more room here. And go ahead and multiply that. So you get a negative 4.9 t squared. We need to divide since they're being multiplied. So you're going to end up doing 0.4 divided by 4.9. Now the object is falling, so our delta y needs to be negative. So that gives you a 0.069 to get rid of that squared, square root. So our time ends up being 0.26 seconds. So that is our time. And that becomes part of our givens. So the horizontal velocity of the rock when Alex tosses it is, so our unknown, whoops, I'm actually not right with my highlighter. Our unknown is now our Vx. So our equation, the only velocity equation we have is delta x equals Vx times t. If we want to go ahead and solve it for Vx, so Vx equals delta x divided by t. We have our delta x, which is 2.4. We just solved for our time, so you just divide those. So you do a 2.4 divided by 0.26, and you get a 9.23 meters per second. So that becomes your velocity in the x, or your horizontal velocity. Next one, the vertical velocity of the rock right before it hits the ground. So that is your final velocity in the y direction. So we're looking for our final velocity. We have two equations with final velocity in it. We don't have our delta y just quite yet. We could solve for it, but let's use our final velocity equals AGT, because we have our time. AG is just a negative 9.8. Our time is 0.26. We plug that into our handy dandy calculator. Vertical y. 9.8 times 6. And you get a negative 2.55 meters per second. So that is your initial, or your final velocity in the y. A horizontal velocity of the rock right before it hits the ground. So we're looking for the horizontal velocity right before it hits the ground. What's so special about your horizontal velocity, your velocity index? It's constant, so it doesn't change. Even the negative does not change. So it's just 9.23 meters per second. So not negative. Do not put negative. It's still going in the same direction. It's being launched. It's still going in the same direction the whole entire time. So your horizontal velocity does not change direction. Okay, here we go. Captain Jack Sparrow was upset because the rum was gone. So he launched a cannonball at a 34-degree angle at a ship that was 34 meters away. It took 5.026 seconds to hit the ship. So that's our givens. So he has a degree. So he gave us the degree at 34. He gave us our delta x, which is also 34 meters. And he gave us our time, which is 5.6 seconds. We always have acceleration due to gravity. So it's asking for the cannon is launched with a velocity of, so we're looking for, when it's asking for that, it's asking for our initial velocity. That becomes our unknown. Our unknown is our VI. So that is your hypotenuse. So you have the angle, it's 34. We're looking for our VI. So we need to figure out our velocity in the x and our initial velocity in the y first. Let's jump down to this question. The horizontal velocity of the cannonball. So we're going to redraw our triangle. Oh, no, not redraw our triangle. Not just quite yet. Please erase. There we go. So this one we're looking for our unknown is our velocity in the x. So our equation for velocity in the x is Vx equals delta x divided by time. We figured that out before. We have our delta x. We have our time. So you just divide them. 34 divided by 5.06. And that gives you a velocity in the x of 6.72 meters per second. So now we have this 6.72 meters per second. That's our velocity in the x. So now we have hypotenuse and adjacent. So we can now use cosine. We can plug in what we're looking for. We have our angle, which is 34. Adjacent is 6.72, and hypotenuse is what we're looking for. Do you ever want what we're looking for on the bottom? Hopefully you just said no, because that's the correct answer. No. Oops, that didn't work. Guess because I had to jump down. Let's go back up. Have to work this way. So you never want what you're looking for on the bottom. So go ahead and multiply both sides by that. So you're left with an initial velocity cosine of 34 equals 6.72. Then we're going to divide. So our initial velocity ends up being 6.72 divided by cosine of 34. 6.72 divided by cosine of 34, and that should give you an 8.11 meters per second. So that is your initial velocity. So the maximum height of the cannon was, so before we need maximum height, we actually need to find our vertical velocity. And we can do that because now we have all three sides. So this is unknown. We're looking for our initial vertical velocity. So we have our initial velocity, which was 8.11. We have our horizontal, which is 6.72. We just need our initial. So you have a couple of choices here. You can do Pythagorean theorem, you can do sine, you can do tangent. I'm going to stick with sine. So our initial velocity just equals VI sine theta. So our VI is 811, sine of our angle, which is 34. So our initial velocity ends up being 11, ends up being 4.53 meters per second. So that is your initial velocity. Then you come up here and do your max height. So your unknown for this one is delta y. You can use delta y equals VIYT plus 1/2 AGT squared. You plug in what you got. So you got 4.53 time is 5.06 plus 1/2 negative 9.8, 5.06 squared. I don't have very much room here, so I'm not going to do all the steps like I usually do. But remember, you got to do this side first, then this side. Do not forget the squared. A lot of people forget the squared. You plug that into your calculator. 2, okay, so it's a negative 5.6, negative 4.3, 22.92, so minus 5.6. You end up getting a negative 102.54 meters. Remember that negative is just telling you direction. So that's how high the cannonball went. So the vertical velocity of the cannon at the top, or at the very, very top, very top, when it starts going down, so your vertical velocity at the top is just 0, and the final vertical velocity before it hits the ground, remember that your initial and final are the same. The final is just negative, so it'll be a negative version of your initial. So a negative version of your initial velocity, and the y, where did it go? Oh, is this one? So it'd just be a negative 4.53 meters per second. One more. Miss Stanforth was jumping on a trampoline. The trampoline is 1.5 meters above the ground. She reaches the top of her jump at 1.3 seconds and performs a backflip. Miss Stanforth reached a maximum height of blank. Don't forget to add your 1.5. So this is just like the other one when you had to, just like the actors. Where is it? Just like the actors when you had to add the 1.3. Now we're having to add the, so we have our trampoline. We have Miss Stanforth, and she's jumping. So what's that saying is that is 1.5 meters above the ground. And then she's going to jump, and that is our delta y, not delta x, delta y. So to get the full answer, get what we're full doing, we're going to have to add these together. So let's pull out our givens. So we do have the 1.5 meters. We have seconds, 30 seconds. We always have acceleration. And our unknown, we're looking for delta y. So our equation we're going to end up using, because her velocity at the top, so basically we're seeing, so if she jumps, she does backflip, let's say she jumps off, so your velocity at the top is 0. So we can make that our initial velocity. So delta y equals initial velocity in the y times t plus 1/2 agt squared. So our delta y, our initial velocity is 0, our time is 1.3 plus 1/2 negative 9.8 times 1.3 squared. 0 times anything gives you a 0. And then you plug that into your handy dandy calculator. Do not forget to squared. Please do not forget to squared. Well, I was looking at a lot of work. A lot of people were forgetting to squared. So that gives you a negative 8.21. Remember that negative is just directional. That's all it is. It's just directional. So we need to, so your delta y ends up being 8.28. We're going to add the 1.5 there. So the whole entire height from ground to top is 9.78 meters. And that becomes your answer. So if you have any questions, please ask Miss Verona or Miss Heath. And have a wonderful time studying. Bye!